In this video, we're going to begin our Unit 4 for college algebra. This is Part 1, Lesson 1. We're going to revisit composite functions as was introduced earlier in the semester. This time we'll go a little bit more in depth. So as a warm-up to this, let's pause the video right now and try to evaluate 1 and 2. Evaluate the function at 3 in number 1, and then evaluate the function at 3x for problem 2. Pause the video now and resume playback in a moment to check your work. Okay, in number 1, f of 3 simply means to change each of these x values in the equation to the number 3 and then simplify. If we were doing this with the calculator, I would expect to see you write down this first step here, and then you could jump to your final answer. That would be fine with the calculator. If you're doing it by hand, of course you want to follow the order of operations. Complete any exponent math first, then any multiplication, and then finally addition and subtraction. For number 2, we're substituting the expression 3x in place of every x value. So we've got 4 minus 2 times the quantity of 3x squared. And again, we'll need to simplify using the order of operations. This is not really something that you can punch into any of our calculators, so this is definitely a no calculator style question. And so when simplifying, again, we're following the order of operations. 3x times itself would produce a 9x squared. Then we can complete the multiplication and combine like terms as possible. No other like terms can combine, so I would say that 4 minus 18x squared is a good solution. Now for part 3, we need to find the domain of the function f of x equals x squared minus 1 over x squared minus 25. And if you recall, the domain is a collection of all x values that can, quote, work or produce real number results from that function. So I'm using the phrase input and output to help describe this composite function description that we're going to talk about in a little bit. But any collection of inputs that produce real number outputs. Now in a quotient or in a fraction, what we're worried about is what happens when the denominator equals 0. So I think in this expression, any x value can be used in the function except for those that make the denominator equal to 0, because of course if the denominator of a fraction equals 0, that means that you're dividing by 0, which produces an undefined result. So for this domain, what I'm going to consider is when does x squared minus 25 equal 0, and I'll make a note here that these are the restrictions. So the restrictions in this particular case are when x squared minus 25 equals 0. And I would prefer to solve any polynomial by factoring if possible, rather than adding 25 and taking a square root. You might find the right answer by doing that, but oftentimes students will take the square root of 25 and report the answer as only 5. But indeed, these solutions are negative 5 and positive 5. Those are our restrictions. So finally, to report this domain, I would say the domain are all x values that are an element of the interval of numbers from negative infinity up to negative 5, from negative 5 to positive 5, and then again from 5 to infinity. You'll recall that with this interval notation, the rounded parentheses mean that that endpoint is not included. So this may look like we're creating a list of numbers from negative infinity to positive infinity, but remember this particular notation does exclude the number negative 5, and then it also excludes the number positive 5. If we were to use set notation, it might look something like this. We would say the domain is the set of all x values such that x is not equal to 5 and x is not equal to negative 5. We could probably simplify that, though, since set notation, at least in our class, is the less formal way to report this. So we might say something like this: x is not allowed to equal negative 5 and 5. Now I do prefer interval notation, but when available or when permitted, set notation would be okay too. Now if we're looking at problem number 1 and also problem number 3 for that matter, these are just simple functions. And with functions, we just sort of have to investigate the behavior of the function to decide what numbers would be off limits or what numbers would be permitted to be used inside that function's domain. But in an example like number 2, we actually placed an entire expression or another function, if you will, inside of another function. That's our composite function behavior. And with composite functions, when asked to find the domain, can be a little bit tricky. Because we're combining two functions and each one contains its own, each one of those component functions contains its own domain, there's a process that we would use to identify the domain of the composite function, and that's shown here, steps 1 through 4. We're going to reuse this process as the weeks progress, or the 2 weeks progress in this particular unit. I just wanted to point that out to you here, that it is at the top of your notes to begin this unit. And again, this hint is helpful to to remember that the domain of a function is the largest set of real numbers for which the function result itself becomes a real number. So what real numbers can we input to produce real numbers as an output? Now, as far as some vocabulary that goes with composite functions, I'm not sure how many of you have seen or used this function notation before with the open circle, but this is what we call composition notation. And it means the exact same thing as using nested parentheses as we're showing over here. And sometimes our textbook and Math Excel switches between the two. So it's important to recognize that this notation here, sometimes called fog notation because it almost looks like the letter O, but this notation simply means to take the function g and place it inside of function f. When read out loud, we would say that f is composed with g. And as we'll see with example A and B down below, order matters when we write the composition instructions. F composed with G is not necessarily the same as G composed with F. Now I also want to point out that in the past we've seen a combination of functions where we actually multiply functions together. And in that case, we had a closed dot, and that would say evaluate the function f at the number 1, evaluate the function g at the number 1, and multiply those two results. And while that worked for what we call combination of functions, that's not what we do with the composition of functions. With composite functions, we stuff one function inside of another, or one function result as the input of the other. So let me show you what I mean here with example A. And this should be familiar. I'm certain you've seen this at one point in the past. If instead of starting with the number 1, let's say we start it with the letter x here, f composed with g at x. What that means is we start with the leftmost equation, that's our outer function, and then we insert our rightmost equation, our inner function. So I'm going to start with, I'm going to say that this is equal to something down here. I'm just going to start with my outer function, 2 times something squared minus 3. That's my outer function, 2 times something squared minus 3. Now the inner function, g of x, which happens to be 4x, that gets placed on the interior of that function f. So we've got f that's on the outside, and technically g that's placed on the inside. And you can do one of two things now that we're being asked to answer f of 1. Well, we could certainly change the letter x to the number 1 at this point and simplify, which I think would be fair to do here. Or you could try to simplify this expression similar to step 2 in that warm-up problem. We could simplify this expression and then change the x to the number 1 at the end. If we were to simplify this as it is, we're left with 2 times 4 squared minus 3, which is 2 times 16 minus 3, which becomes 32 minus 3, and we end up with 29. 9. If we had simplified this expression, we might end up with 2 times 16x squared minus 3, which is equal to 32x squared minus 3. And then if we substitute the number 1, 32 times 1 squared minus 3, we end up with 32 times 1 minus 3, 32 minus 3, and then ultimately 29 again. I prefer this method here when we have several computations to complete. If we're composing f with g at 1 and then some other numbers after that, I would most definitely want to simplify the expression first. But if it's a single value and we're computing one composite result, then really it makes no difference which method you choose. So I'm going to erase this one to get it out of the way of part B. And I'm going to ask you to pause the video and try part B on your own. Resume playback in a moment to check your work. And in sticking with the green and black theme here, G is marked with a green ink and F was marked with black ink. So we've got this outer function 4 times something. The something on the inside ended up being the entire function f, 2x squared minus 3. I did elect to substitute x with 1 back here and then simplify and ended up with a solution of -4. And so hopefully that's enough to prove to you or show you, anecdotally anyway, that these two are not necessarily equal to one another. F composed with G at some number is not always going to be G composed with F at that same number. Sometimes it does happen, but not always, so we can't rely on that. With part C and D, we're going to compose a function with itself. In this case, F, we again have the expression 2 times something squared minus 3. It just turns out that our inner function is the 2x squared minus 3 again. Now, we're not going to do several of these computations, so I think I will make the replacement all the way back here at the beginning. We're going to evaluate this at -2 and then simplify. Make sure that you follow the order of operations correctly here when simplifying this if you're doing this by hand. Certainly this is an expression that we could enter into a calculator, and as long as it follows the order of operations, you'll obtain a correct result. But on a no calculator portion of the test, you want to be absolutely certain that you're doing your math correctly. So I'm focusing on the parentheses, and I'm going to the innermost parentheses first. There's nothing I can do to simplify that, but I can move to the exponent surrounding it. -2 squared is +4. Then I'll copy the rest of the expression down without making any changes. I don't want to get ahead of myself. I'm still inside this grouping symbol, so I can do the multiplication before any addition and subtraction. So we'll call this 8 minus 3, quantity squared, minus 3. Then 8 minus 3 is 5. Now 5 squared will complete the exponent next. Then multiplication, and then finally addition and or subtraction. Of course, it would help if I could do my mental math correctly. 2 times 25 is not 75, but 50. Let's try that again. 50 minus 3 is 47. There we go. Let's go ahead and try part D now on your own, please. Pause the video and resume playback in a moment to check your work. And that one shouldn't have been too challenging. We ended up with -16 as a result. For additional practice, I would challenge you to complete these problems 11 through 20. Now I know that you've got lots of Math Excel work to do, but these again would be good practice as well. If you do complete these and would like to check your work, I'll have an answer key available to these problems that I can send to you in an email as a PDF document. Or if you're working on these and you have a question on any one, send me a message and I'll be happy to address that for you. Now sometimes we experience composite functions in situations in which the functions themselves aren't well defined or aren't clearly defined. And one thing that comes to mind is this notion of operating a car with adaptive cruise control. If you've got your car that's trying to, hold a steady speed, let's say 50 miles per hour, well, the car has to go through all sorts of calculations and computations in order to make that happen. How much fuel has to be delivered, what gear the car has to be placed in, etc. But if using adaptive cruise control and all of a sudden another vehicle jumps in front of you, well, that vehicle will then in turn affect how your vehicle operates its cruise control. It may not maintain this 50 miles per hour, but it might change based on the input that it receives from its sensors as it's looking around the car. And we don't know what the functions are or what work is being done into computing the adaptive cruise settings, but that's kind of an idea. We tend to respond to different inputs and then adjust our outputs accordingly. So in a more pure mathematical sense, we've got a series of practice problems here. While I have not defined what f of x is or g of x, we can't calculate the result of f of x or g of x because we don't have the formula associated with them, but we can perform many of these tasks. All of these input-output results can be determined from the table that's supplied. So if we look at practice problem A, for example, we are being asked to compose f with g at 1. Now I'm writing it with this notation here, the nested notation, so that you can see that the two are equivalent, and just to remind you that this is an appropriate form of notation. If you look carefully, it kind of looks like we have this function notation for f on the outside and then the function notation for g on the inside. And so if I were to evaluate this, well, the function f is going to be applied to some result that we get for g at 1. Now, using this table, I'm going to find 1 on the x input row, and then I'm going to look down to the g line and find out what the output is for g. So when x is 1, the output for g is 0. And it's the output of the g function that now becomes the input of the f function. And since we have this result 0, now I can evaluate this function f at 0. And now when I look for the function result for f at 0, I get an end result of -1. So f composed with g at 1 ends up equaling -1. For part B, we see something quite similar, f composed with g at -1. So f composed with g at -1 implies that we should evaluate g at -1 first, our inner function, and then take that result and use that as the input for our outer function. So g composed at -1, and I'm going to erase this so that it doesn't get too messy here. G composed at -1 ends up being 0 as it was before. That's kind of interesting. And now we evaluate f at 0, and that also comes out to be -1 because f evaluated at 0, we already saw this once before, is -1. For part C, we're being asked to compose g with f at -1. Whoops, I meant to change my colors there. With f at -1. So the outer function g, we'll worry about that in just a second. Let's first compute the inner function result, f at -1. Well, if I start at -1 for my x value, the result for function f is -3. Now I can evaluate the function g at an input of -3, and we get an end result of 8. I'd like for you to try D, E, and F on your own now. Please do so. Pause the video and resume playback in a moment to check your work. And here's what I would expect to see as a result for D, E, and F. Now I know that many of you can read this chart and kind of move around this chart with arrows and that sort of thing, and you can read the chart and find a final answer, but recall that many of the questions that I ask you to complete on tests or quizzes, I do want to see evidence of your work, or at least an explanation of how you obtained a result. And even though, again, we can answer these by simply looking at the chart, leaving this amount of work, I think, would be appropriate to show evidence of your understanding. Now, in a similar method to the last example, we can find the results of composite functions by looking at the data points on a graph, or interpreting a graph for each of those data points. So in question A, we need to find G composed with F at -1. Well, F evaluated at -1 requires us to look at the function f of x, which is this line here. There's f of x. And then the result from that function will end up being the input for g of x, which is this curved line here. So if we're going to start with -1, we're going to go to -1 on the x-axis, and we're going to look for the y result associated with it. This is not a table of data, but a graph of data, and we're being shown that f evaluated at -1 ended up equaling +1. And since f at -1 equaled +1, that +1 now becomes our input for the g function. And when we run to the x value of 1, we can look up to note the y value associated with that position, and that happens to be 4. So we can say that the end result here, g composed with f at -1, happens to be 4. And here's the evidence that we could leave that shows how we found our solution. For g composed with f at 0, we must evaluate g at the result of f of 0. Well, f of 0 is 0 itself, because the y result at this position is 0. Now, when I use the x value of 0 as the input, the y value result here ends up being 5. So g composed with f at 0 is 5. Please try C and D on your own and resume playback in a moment to check your work. And again, based on the positions of our coordinates in each function, I would expect these results for C and D. I think I'm going to make another video following this one that more specifically addresses the domain of composite functions, rather than adding it on to the end of this one here. So we'll go ahead and skip 21 and 22 from today's notes and instead pick that up with the next video. So thanks for watching.